we have a look yesterday basically is on the definition of corrosion. Okay, and we know that corrosion is basically the degradation of materials, one of the degradation of materials, usually a metal, by chemical or electrochemical reaction with its environment. So as I told you, the environment that we are talking about here is the presence of oxygens, water, presence of any impurities, anionic impurities, chloride ions, for example, pH, relative humidity, and whatsoever. Corrosion process is also a spontaneous process. Always remember that the delta G will be negative in value. And why actually metals tends to corrode naturally is because it is thermodynamically unstable in the current form. Therefore, there's a drive force making the metal easily to react with the environment to produce a more stable product like rust, metal oxide, and others. Okay. And actually, I've told you that corrosion can be controlled via, I think, 5 major techniques. Okay, so we are going to look into this detail, I think, in the next few subchapter. And part of it is actually on the corrosion process. We have dry corrosion, which actually represents the corrosion process that occurs in a dry condition. This is actually in the case of with the presence of oxygen gas, other types of vapor. And the most common one is actually wet corrosion, where the metal has been soaked or dipped or immersed in water, and water actually functions as the electrolyte. The corrosion reaction itself is a redox process, as I told you, okay, where the oxidation process occurs at the anode terminality and the reduction process occurs at the cathode terminality, right? And I think part of it depends on the environment that we are talking about. For example, if we are talking about the environment in the acidic solution, so you know that the reduction process will be different. And then I guess we also have looked into the formation of rust on the corrosion chemistry of iron, where the first reaction occurs by the formation of Fe2+, and then after that the reduction process. And finally, the first rust product produced is actually known to be ferrous hydroxide. And then it further oxidized because it's definitely not stable enough. Further oxidized to form a more stable Fe3 that is called as ferric hydroxide. And before we end, actually, we have looked into some possibilities of forming different types of rust product. These actually, of course, depends on the amount or the concentration of oxygen, water, pH, and whatsoever. Of course, the initial products that you will produce is a ferrous hydroxide or ferric hydroxide, but further oxidation could produce oxyhydroxides and other types of metal oxides. In this case, for oxyhydroxides, excuse me for the spelling mistake over here, it should be oxy, okay, so oxyhydroxide, you have alpha, beta, delta, and gamma. All these are actually the same polymorph, but it has a different crystal structure. Okay, so because of different crystal structure, then it is actually having a different plane, different lattice. Then the name is actually different. So alpha is always related with geotite, beta is acaganite, delta ferroxide, and gamma is lepidoprosite. You can have magnetite as the type of the metal oxide or the iron oxide that forms Fe3 or 4. This is actually magnetite, and the appearance of this magnetite is actually black in color. Okay, and you can have ferric hydroxides and hydrated ferric hydroxides. So this actually depends on. Normally, it forms hydrated. It means that it absorbs water, and it will be like slightly wet in condition. And the formation of all these products can be formed layer by layer, depends on the first formation of products, you can have like formation of ferrous hydroxide first, and then after that, further oxidation forms another layer of ferric hydroxides and oxyhydroxides. And then after that, going downwards, you can have, I think, another types of, I think, products. Like, for example, here, magnetite, you see black in color. And today we are going to look into the reaction feasibility. Of course, in the first the first slide, I have explained that for corrosion process, it is a spontaneous process, which means the delta G value is negative. Okay, and I think due to that, the E cell or the standard potential must be positive in order to have a spontaneous process. Imagine that right now you have zinc immersed in hydrochloric acid, and you know that zinc will be oxidized to form zinc 2 plus, and since this in acid, so H plus is going to be reduced to form H2, hydrogen gas. Okay, so the correlation between the standard potential, so you know that the standard potential can be calculated. Okay, here, oops, sorry, standard potential E cell or E naught cell is equals to E naught cathode minus E naught anode. Okay, so this is actually in the standard condition. Remember that standard condition, it means because you have naught over here, NOUGHT naught, and AUGHT. So naught actually means that it is in the standard condition. So what does it mean by standard condition? It means that the reaction occurs at temperature 35 degrees Celsius, pressure is equals to 1 atm, okay, and concentration is equals to 1 molar. But if it is not being monitored in the standard condition, then we will use Nernst equation to calculate. So for Nernst equation, I'm sure that you've heard about Nernst equation. Okay. And then the correlation between standard potential and free energy can be calculated using Faraday's equation. So this is actually known to be Faraday equation, where it relates energy with standard potential. So you have delta G is equals to minus NF multiplied with delta E. So N is actually the valency number. F is actually Faraday constant. Faraday's constant is equals to 96,500 coulombs. Okay. And delta E is actually the standard potential in voltage. So this is what I'm talking to you just now. If the process actually happens not in the standard condition, not in 25 degree, not in 1 atm, not in 1 molar, then you will use Nernst equation to calculate the standard potential. So a standard potential in a non-standard condition can be calculated as follows. E cell is equals to E naught cell plus with 2RT over NF log product over reactant. Okay. Right. So in this case, you can have a variation of Nernst equation. I guess don't be confused. Sometimes you will see like over here, okay, over here you will see that it is product over. Oh, sorry, this is actually not product. This is actually reactant. Reactant over product. And you might see also equation of Nernst where it shows products over reactant. So what's the difference? Okay, so you might confuse. But the main thing is actually this is just mathematical representation. Please note on this symbol. If it is a plus symbol, then it means that it is actually in opposite. The most common that you will see is actually negative or minus. So E cell equals to E naught cell minus 2R 2.3 RT over NF log products over reactant. So this is the one that you've seen a lot. And you notice that this one is actually minus. So don't be confused. I guess maybe I've seen a lot. I mean, like even in the degree level, you already being confused with this simple symbol, mathematical reasoning. Okay, right. So the Nernst representation of a hydrogen ion reduction can be shown as follows. Over here, we can actually relate Nernst equation with pH. Okay, so the representation as follows. And anyone knows what will be the equivalence of pH? pH is equal to what actually? Siapa tahu? Anyone can tell me. You maybe seen this in analytical chemistry, KAT 259 or 245, forgot. Fatin Nordini ada. pH is equal to what? Fatin?
Come again, Doctor.
Okay. So pH is equal to what? How did you calculate pH actually? Did you see this representation I show you, right? The Nernst equation of hydrogen ion reduction, and somewhere over here you notice there is a pH. Not sure. You know about this, but maybe you forgot.
Yeah, I forgot.
pH is actually equals to negative log delta H. Negative log H. H is actually the concentration of H plus or acid. You can calculate pH by using this formula. I think you've seen this or you know this during your maybe matriculation or STPM. So tak boleh kata tak tahulah. This is actually the most simplest way. How you actually calculate the strength of acid is actually by calculating negative log of the concentration of H plus. Okay. So if you substitute over here, you'll see that it will become minus 0.059 negative log H plus. Okay. And negative become plus. And another thing is, you will also see that over here, it is noted as 2.303 or what, RT. And over here, it is noted as 0.059. Okay, so what's actually the difference? Actually, another difference, as I said, this is just a mathematical reasoning. Okay, you might see in this, sometimes they use log, sometimes they use ln. So for a natural log, okay, it will be equals to a value because you know that 2.303 is actually equals to log 0. So that is why you can have a variation of 2.3 or sometimes 0.059. These actually have been calculated with the gas standards and also gas constant and also the temperature. Right. So today we are going to look at how we determine corrosion rate. It is always essential to know that whenever we want to observe how fast the corrosion process occurs, we are actually not looking at by observation of the surface, but we are actually looking at the value, how fast the process happened. So in order to monitor, so people are actually using different methods, and part of it is actually to monitor the corrosion rate using a wet loss method. Okay, so in wet loss method, okay, it is a simple method. Wet loss, where you have a plate that you immerse in the solution with time 0 and the weight initial A. You know what is actually the weight initial. And after a certain time, okay, the metal will of course be corroded. You have a weight final of B. Okay, so in the end of the day, you can have weight loss, which is equals to A minus B. So this is actually the weight loss, okay, at a certain emission time. So this is actually the most common techniques, which is very simple, even though we can also use electrochemical techniques or whatsoever to calculate corrosion rate, but this is the most easiest one. Okay, all right. So the corrosion rate determination can be noted as follows. There's formula to calculate it. Okay, so you have the first formula over here. R is actually corrosion rate in the unit of MPY. So MPY is actually mils or miles of penetration per year. Miles. Miles is actually a distant unit lah. Okay, or it is actually equals to inches, 0.001 inches of penetration per year. So RMPY is equals to 534. So if you ask me why it is 534, this is a standard standard values. Okay, and W is actually the weight loss in milligram over rho. Rho is actually the density of the metal. Okay, A is actually the area of the specimen area in inches, and then multiply with time of immersion in hours. Okay, and how actually you are going to monitor. If let's say that if you use this formula, you're observing a value with, lesser than 1 mils per year, then this is actually outstanding. It means that the metal doesn't corrode much, no corrosion, or very slow corrosion. If the value is in between 20 to 50, then we'll see this actually having a moderate corrosion. And then if it is actually larger than 50, then we can see this as severe corrosion. Right? So this is also another formula, Faraday's law. Again, Faraday formula. I think earlier we have a Faraday equation, delta G equals to NF minus NF over delta E. But this one is actually a Faraday law to relate weight loss with current. Okay, with current value. Right. So what would be the formula? This is actually something that you need to remember. These two things, these two equations. It's very much important. Need to remember it. Okay. So what did Faraday say? For metal loss, M, it is actually equals to Q is actually the charge. So charge is actually equals to charge Q is equals to current multiplied with time. Okay, so if you actually expand it, you will get I T MW. MW is actually the atomic mass of the metal divided with N. N is actually the valency. F is actually the Faraday's constant. Let me write it here. I is actually current in amperes. Okay, T is actually time in second. MW or MA is actually the atomic mass. In gram over mole, right? N is actually valency. So what is valency? Valency is actually the value, like Fe, you know that Fe, the valency is equal to 2 plus, copper is equal to 2 plus, aluminium is equal to 3 plus, zinc is equal to 2 plus. Okay, so all these are actually the common metals, valency. And F is actually the Faraday's constant, 96,500 coulombs. Right. And from the metal loss, you can calculate corrosion rate, okay, with the correlation of current. Therefore, corrosion rate in MMPY, millimoles per year, is equals to mass loss over area times with time and density, or it is also equivalent to small I. So what is small I? Okay, if you remember back in electrical properties, so small I is actually equals to current density. So what does it mean by current density? Current density, it means that it is actually current over area. Okay, current in amperes over area in centimeter square. Right? Then you can have current density multiplied with MW over rho and F. So how actually you can get this? Okay. So basically you can get this by expanding these terms. From here. Okay. If you substitute, you will have capital I, which in the end over area. So current over area, as I said, it equals to current density. So that is why you have a substitute over here. Okay, so MW will remain. Okay, time with time will cancel off and leaving out the rho and F. So that is why it will be simplified and you get this. You can either calculate corrosion rate if you have a mass loss over area times time and also density, or you can also use this formula as well. You find what will be the current density and you actually multiply it with molecular or atomic mass over density times valency and also Faraday's constant. Right. So another term that you need to understand is actually the conversion to another unit. So obviously from here we've seen miles per year as a 1 unit. Remember, you are going to use this formula if you don't want to relate it with current. And please notice that the unit is also different. Over here we use milligram, here gram over centimeter cube. Area is actually in inch and time is actually in hours. There is a clear difference between this formula with the Faraday's law that we are, I think, talking about right now. Okay, so in Faraday's law, the unit of corrosion rate is actually in mmPy, millimoles per year. Okay, if let's say that you obtain a value from here, MPY, and you want to convert it into MPY, it is not by simply multiply it with 10 power of negative 3, because it wouldn't do. If you assume that it is in milli and multiply with 10 power of minus 3, then it is not working. It is actually looking at this conversion table. So we have a different sets of unit conversion. For example, if let's say that the corrosion rate is calculated using potential stat, electrochemical techniques, you will get a value in milliamperes over centimeter square. Okay, if you want to convert it into mmPy or millimoles per year, then you have to multiply with a factor. So the factor will be this 3.28. If you want to convert milliamperes over centimeter square to MPY, then you need to multiply with 129. If let's say that from MMPY, you need to convert to MPY, then you I think multiply with 39.4. So from MMPY to MPY, so MMPY you need to multiply with 0.0254. So obviously this something that you need to remember, but I don't think that you have to remember all. What is important is to remember this value and also this value. Okay, conversion of MPY to MMPY or MMPY to MPY. Okay, these are actually the important values that you need to memorize. To convert MPY to MMPY, you need to multiply with 0.0254. Sorry. And to convert MMPY to MPY, you need to multiply with 39.4. Okay. So this is actually the examples. You have metals that have a valency of 2, atomic mass of 55.85, density that is equals to 7.88 grams over centimeter cube. If you want to convert into I think conversion, if let's say that it produce corrosion rate of using potential set equals to 1 milliamperes over centimeter square, then it is actually equivalent to 11.6 MMPY. It's also equivalent to 456 MPY and also equivalent to 249 gram over meter square over day. Okay, so we are going to look at these examples, few examples. The first one, suppose that in a cell, it composed of copper and zinc. The density at the copper electrode is 0.05 amperes over centimeter square. The area of both copper and zinc electrode is equals to 100 centimeters square. First, calculate the corrosion current. Second, calculate the current density at the zinc anode. And finally, to calculate the zinc loss per hour. Okay? All right. So there's a lot of question over here, but we need to understand what is actually the theory behind it. So you have a cell, okay? You have copper and you have zinc. It is connected together, okay? So if I ask you which one will be anode, which one will be cathode, siapa tahu? This is a very simple, I think, tricks. Liu Lijing, are you there?
Yes, doctor.
Okay, Lijing. If you have a pairing between copper and also zinc, which one will be anode, which one will be cathode?
Anode will be copper.
Anode will be copper.
Yeah.
Confident? Okay. It's okay. Thank you very much for trying. Next, I just want to check with Nur Anis. Nur Anis. Anis Afrina.
Yeah.
Anis. Antara copper and zinc, which one will be anode, which one will be cathode? It's basic electrochemistry.
Yes, anode.
Sorry, yang mana satu anode?
Zinc.
Zinc anode. Okay, tadi Li Jing cakap copper akan jadi anode, and then Anis cakap zinc akan jadi anode. So what's the justification?
Sebab zinc akan lose electron.
Okay. Basically, in order to determine the terminality of metals, if you have a pairing like this, we have to look on the standard potential value. This is actually the important. You've learned about this, okay, electrochemical series. We know that for zinc, the standard potential is equal to 0.7 volt, and for copper is equal to plus 0.2 volt. It's a clear difference that you see this value is very much, I think, have a difference, a large difference. Okay, always remember that the more negative potential, it tends to oxidize easily, or meaning that it is more reactive, and this will tend to become anode. The one that is more positive, it tends to reduce because it is non-active, and this will become cathode. Obviously, when you have copper and zinc, okay, so zinc will be anode and copper will be cathode. Right. So I hope it's understood now. The area that they are saying is that both are having the same area. Okay, 100 centimeters square. So area 100, area here also 100. Okay. All right. So the current density at cathode copper, okay, is 0.5. Kat sini dia dah beritahu dah, copper is cathode. Okay. All right. So 0.05 amperes over centimeter square. So the first question is actually to calculate current, corrosion current. Okay. As we know, current density is equals to current over area, isn't it? So in order to calculate current, this equals to current density multiplied with area. So current density berapa? 0.05 multiplied with area is equals to 100. Then you get 5 amperes. Faham tak? Alright. Next question. Current density at zinc anode. Okay. So the current value produced, okay, from anode to cathode. Okay. The current value produced is 5 amperes. So the question now is what will be the current density at the zinc anode? So current density, still the same, current over area. So current is equal to 5 divided by area, 100. Then you get, again, 0.05 amperes over centimeter square. Okay? So what does it mean? If you have a similar area and it will actually produce a similar current value for the cell. And if, let's say over here, the areas is similar, then you will get the current density value is also similar. And finally, okay, the mass loss, because it says the zinc loss per hour. Okay. So what would be the formula just now? Zinc loss, metal loss. M is equals to what? Okay. IT MW over NF. This is actually the formula using Faraday's law. Current value, we already have 5. T is actually the time. Okay, so time should be in second. Remember, time in seconds. And in this question, it says that it is per hour, 1 hour. Okay. Time should be in second. So we have to calculate, I think we have to convert 1 hour into second. Okay, just want to check. 1 hour have how many minutes? Berapa minit? 1 jam ada berapa minit? Nur Syahira, Syahar. 1 jam ada berapa minit? Soalan senang je. Syahira.
Ya, Doktor. Ya.
1 jam berapa minit?
60.
Okey, Syahira, stay. 60 minit. 1 minit ada berapa saat?
1 minit 20 saat. 1.20.
1.20? Mak weh.
1 minit 60 juga.
60 second. Okay, so you want to convert 1 hour, hour into second. Okay, so it's going to be 60 times 60. Then, sebab tu you akan dapat 3,600 second. Betul tak? Okay, right. So over here, I think information is not given for the atomic mass for zinc, but this is actually the value. 95.38 gram per mole. Valency of zinc is equals to 2 and 96,500 coulomb is actually the Faraday constant. If you substitute all these values together, you will get it is actually equal to 6.1 gram. 6.1 gram. This is not actually per hour of unit, but this is actually the 61 gram of zinc lost in 1 hour. Okay. I hope this one is quite clear to you guys lah. Lain. Okay. We are going to look at other examples also after this, before we end. Okay, so as I said just now, in order to determine which one is anode, which one is cathode, it is important to look at the standard electrochemical series, or EMF series. EMF stands for what? Electromotive force. Okay, daya gerak elektrik lah. Electromotion force or electromotive force, EMF. But this is actually the electrochemical series lah, because you know that it is actually been assigned in the standard potential values. Okay. So just now I think we look at copper. Copper tadi saya cakap 0.2 or 0.3 positive. And then you have zinc. Zinc is minus 0.7. Is more negative. So more negative potential will be more reactive. And it will become anode rather than cathode. Okay. The one at the top will be more positive. Then it is less reactive. Noble lah, kita cakap. This one is noble region, this one is active region. So it will tend to become cathode. You learn this, I think, in high school or whatsoever lah. So you should know. It's just, I think, revision lah. So similarly, if we are talking about alloys, alloys also have its own series. We call it as galvanic series. And you can see from there which one will be more noble. Of course, stainless steel, and the one that is less corroded will be cathode, and then the one that is more active will become anode. Right. So last example, okay, before we end. So we have iron container, 10 cm times 10 cm at the base. At its base, filled to a height of 20 centimeter with a corrosive liquid. A current is produced as a result of electrolytic cell. After 4 weeks, the container has decreased in weight by 70 grams. One, calculate the current. Second, to calculate the current density involved in the corrosion of iron. So, I think to answer this question, it is easier for us to imagine. Okay, so we have a container. So you have a container with a base of 10 times 10, and then it is actually been filled with liquid, corrosive liquid. Okay, filled with 20 centimeters in height. Okay, so we assume that this container is an open lid, terbuka. Okay, and the corrosive, I think, region will be at the sides, at the sides of the container. Right. So what other information it gives? Time is actually equals to 4 weeks. Okay. Mass loss is equals to 70 gram. Okay. So other information that is not provided, maybe I can give. Atomic mass, 55.85 gram over mole. Okay. Valency is equal to 2. What else? Density. Okay, so density is 7.85. Or at 7. Gram over centimeter cube. So first question, we want to calculate current. Mass loss is equals to I TMW over what? Over NF. So always remember this formula. Okay, so we want to rearrange now. Current will become equals to mass loss multiplied with NF over time molecular weight. Okay, and time we have to change into second, right? So 1 week equals to how many days? 7 days. 1 day equals to 24 hours. 1 hour equals to 3,600 seconds. So the unit conversion of this one will be 4 times with 7 times with 24 times with 3,600 second, then you will get, I think, equals to 2.42 times 10 power of 6 second. This is how you convert the unit for time. And then we just substitute 70 multiply with 2 multiply with 96,500 over 2.42 times 10 power of 6 times with 55.85. Okay. Then we will get 0.1 amperes. Okay. Now, current density. So current density, we know that current over area. Okay. So we already got current. We want to find area. So looking at this dimension, so how, as I said, the corrosion will occur at the sides and also in the bottom. In order to calculate the area, you have to calculate the sides. So sides, area is equals to, you have like 4 sides plus with 1 base. So sides 4 times with 10 times 20 plus with 1 base 10 times 10. Then you get it's equal to 900 centimeters square. Current density, therefore, it will be 0.1 over 900 centimeters square, which will be equals to 1.1 times 10 power of minus 4 amperes over centimeter square. Okay? All right. So perhaps maybe tomorrow I will give also another examples for you guys to see. Okay? Another, I think, examples on calculating corrosion rate in a various dimension, in a pipe or in a cone or whatsoever. But things that you need to remember is to calculate area. You should know how to calculate the area with a fixed or different types of dimension. Okay, so factors affecting corrosion, I guess this one we are going to continue it tomorrow. Okay, so before that, is there any questions so far? Anything that you want to ask before we end our lecture? Very short today. Okay, so inshallah tomorrow we are going to have your last quiz. Okay, all right. So I think I will stay back if you guys have another question. But if you don't, then I would like to thank everyone for attending this morning class for today. I really appreciate it. And with that, thank you very much. And Assalamualaikum warahmatullahi wabarakatuh. See you tomorrow.